Polaritons are fascinating in fundamental physics because they exhibit properties of both light and matter, enabling unique behaviors and interactions that aren't possible with pure light or pure matter alone. This dual nature allows polaritons to explore new quantum states and phenomena. For instance, they can form Bose-Einstein condensates at relatively high temperatures compared to atoms, providing insights into quantum mechanics and phase transitions. Moreover, polaritons can help us understand strong coupling regimes and the interactions between light and matter, offering potential breakthroughs in quantum information science, materials science, and nanotechnology. Their study bridges different areas of physics, contributing to a deeper understanding of the fundamental principles governing the universe. Polaritons are special particles created when light, photons, interacts strongly with matter, excitons, in certain materials. Polaritonics is a branch of science that deals with polaritons, which are quasiparticles resulting from the strong coupling of photons, particles of light, with excitons, quasiparticles representing an electron bound to an electron hole in a semiconductor. To understand this better, let's break down these concepts with examples and analogies. Polaritons. Think of polaritons as hybrid particles. They are part light, photon, and part matter, exciton. Imagine a child on a playground swing. The swing's motion can be seen as a mix of the child's movement and the swing's own natural motion. Similarly, a polariton is a mix of the properties of photons and excitons. Photons. These are the basic units of light. When you switch on a flashlight, photons are what travel out from the bulb to light up a room. Excitons. These are created in semiconductors when an electron absorbs energy and moves to a higher energy level, leaving behind a hole where it used to be. This electron-hole pair behaves as a single entity. Creating polaritons. When photons are trapped in a material and interact strongly with excitons, they can combine to form polaritons. Imagine you're at a concert where the audience starts clapping in sync with the music. Here, the clapping, photon, and the music, exciton, merge to create a unique concert experience, polariton. A practical example of polaritonics is in the development of polariton lasers. Unlike traditional lasers, which rely solely on the energy of electrons, polariton lasers use the hybrid nature of polaritons to produce light more efficiently. This could lead to advancements in everything from telecommunications to medical devices. Exciton polaritons arise from the interaction of light with excitons, which are bound states of electrons and holes in semiconductors. Phonon polaritons are formed when light couples with phonons, which represent vibrations in the crystal lattice of a material. And finally, Plasmon polaritons emerge from the interplay between light and plasmons, which are collective oscillations of electrons in a metal. This diversity in their nature allows polaritons to exhibit a remarkable range of properties and behaviors. Understanding these intricacies is key to unlocking the potential of polaritonics. To truly grasp the essence of polaritons, we must venture into the realm of quantum mechanics. In this strange and counterintuitive world, particles cease to be tiny billiard balls and instead become waves, their existence smeared out across space and time. Polaritons, true to their quantum nature, are described by a peculiar blend of light and matter waves. Imagine a single entity embodying both the wave-like nature of light and the particle-like behavior of matter. This duality is at the heart of polariton behavior. Their unique nature grants polaritons an intriguing characteristic. They can travel over significant distances like light while simultaneously interacting strongly with matter. This intriguing combination opens up exciting possibilities for controlling and manipulating light in ways never before imagined. The key to understanding the behavior of polaritons lies in their dispersion relations, which describe how their energy changes with momentum. When plotted on a graph, these relations reveal the unique energy-momentum landscape that these quasi-particles inhabit. The strength of the interaction between light and matter dictates the nature of polaritons. In the realm of strong coupling, the interaction is so intense that light and matter cease to exist as separate entities, merging to form these hybrid particles. Conversely, in weak coupling, the interaction is more subdued, leading to a less dramatic interplay where light and matter maintain their individual identities while still influencing each other's behavior. The seeds of polaritonics were sown in the 1950s when the concept of these hybrid light-matter particles was first theorized. However, it wasn't until the 1990s that this field truly blossomed. A pivotal breakthrough occurred with the creation of exciton polaritons in semiconductor microcavities, These tiny structures, meticulously designed to confine light within a confined space, provided the perfect environment for light and matter to engage in a delicate dance, leading to the formation of these fascinating quasi-particles. The creation of Exciton Polaritons marked a turning point in the field. It provided concrete evidence for the existence of these hybrid particles and opened the floodgates for further investigation and exploration. Since then, the field has witnessed an explosion of research, with scientists around the globe unraveling the mysteries of polaritons and harnessing their potential for a wide range of applications. From revolutionizing computing to transforming optics, the future of polaritonics shines brightly, promising groundbreaking advancements in diverse fields. Join us as we journey further into this captivating realm, exploring the intricate physics, diverse types, and groundbreaking applications of these fascinating quasi-particles. To comprehend polaritons, we delve into quantum mechanics, where particles like photons exist as both particles and waves. Imagine a photon as a rippling wave, its existence spread over space and time. When these waves encounter matter, a fascinating interplay ensues. It's as if the photon and the exciton engage in a delicate dance, forming a new entity. This quantum dance lies at the heart of polariton formation. Polaritons inherit properties from both light and matter, fueling excitement for their potential applications. To navigate the world of polaritons, we need a map, a guide to understand their behavior and predict their movements. This map comes in the form of dispersion relations, graphical representations that reveal the intricate relationship between a polariton's energy and its momentum. Think of it as a topographic map, but instead of mountains and valleys, we have peaks and troughs representing the energy landscape that these quasi-particles inhabit. These dispersion curves are not mere abstract concepts. They hold the key to unlocking the secrets of polariton behavior. The shape of these curves dictates how polaritons propagate, interact with their surroundings, and even condense into exotic states of matter. A steep curve signifies a strong dependence of energy on momentum, while a shallow curve indicates a weaker dependence. For instance, the dispersion relation of an exciton polariton reveals a characteristic anti-crossing behavior, a telltale sign of the strong coupling between light and matter. This unique feature arises from the interplay between the photon's tendency to travel at the speed of light and the exciton's tendency to behave as a massive particle. The resulting hybrid particle navigates this tension by adjusting its energy and momentum accordingly, leading to the observed anti-crossing in the dispersion relation. Understanding these energy landscapes is crucial for manipulating polaritons and harnessing their potential. By carefully engineering the properties of the materials and structures that host these quasi-particles, we can tailor their dispersion relations, dictating their behavior and guiding them toward specific tasks. The interaction between light and matter exists on a spectrum, from fleeting encounters to intense embraces. In polaritonics, this interaction strength dictates the nature of the quasi-particles formed. We categorize these interactions into strong and weak coupling regimes. In strong coupling, light and matter merge into a new entity, the polariton. Their interaction is so intense, they become a single, harmonious entity. This regime is where polaritons exhibit their most intriguing properties. In weak coupling, the interaction is more subdued, less passionate. Light and matter influence each other, but remain distinct. Weak coupling governs light absorption and emission, influencing optical properties. Imagine a semiconductor, teetering on the edge of conductivity. Electrons, tiny carriers of negative charge, dance around, seeking equilibrium. A photon strikes, knocking an electron loose, creating a hole. The electron and hole form a fleeting partnership, an exciton. The exciton can recombine, releasing energy as light. In a microcavity, photons interact with excitons, forming exciton polaritons. Exciton polaritons blend light and matter, promising remarkable properties. The microcavity, a stage for quantum interactions. Imagine two highly reflective mirrors, separated by a minuscule gap. This gap traps photons, bouncing back and forth. A thin layer of semiconductor material resides within. Photons stream in, encountering excitons. This quantum dance gives rise to exciton polaritons. Scientists can fine-tune this interaction, opening up exciting possibilities. Probing the secrets of Exciton polaritons. Unveiling Exciton polaritons requires sophisticated techniques to probe the quantum world. Imagine a laser shining onto a microcavity where exciton polaritons perform. The laser resonates with excitons, forming hybrid light-matter particles. These particles emit light, revealing their presence. This light, or photoluminescence, reveals their properties. Scientists capture and analyze this glow to decipher exciton polaritons. Techniques like angle-resolved photoluminescence spectroscopy map their behavior. These tools and models unravel exciton polaritons' mysteries. Plasmon polaritons, merging light with metallic waves. Our journey into the realm of polaritonics now leads us to the interface of light and metal, where a different kind of hybrid particle emerges, the Plasmon polariton. Imagine a smooth, gleaming metal surface, its electrons flowing freely like a vast, undulating sea. When light, with its oscillating electric field, strikes this metallic surface, it sets the electrons in motion, creating ripples of charge density that propagate along the interface. These ripples, known as surface plasmons, are collective oscillations of electrons, akin to waves on the surface of the ocean. However, unlike ocean waves that dissipate their energy as they crash upon the shore, surface plasmons can couple with the incident light, their destinies intertwining to form a new entity, the surface Plasmon polariton. This hybrid particle inherits characteristics from both its parents. From the photon, it gains its ability to transport energy and information, while from the surface plasmon, it acquires the remarkable ability to confine light to dimensions far smaller than its wavelength. This confinement, this squeezing of light into nanoscale volumes, is one of the most intriguing aspects of surface Plasmon polaritons. It opens up exciting possibilities for manipulating light at scales far below the diffraction limit, the fundamental limit that typically restricts the size of optical components. Imagine crafting optical circuits and devices with components mere nanometers in size, shrinking the entire field of optics down to the nanoscale. This is the promise of plasmonics, the field that seeks to harness the unique properties of surface Plasmon polaritons. Metamaterials, sculpting light with artificial structures. Scientists have turned to metamaterials to control light in extraordinary ways. These materials, with intricate structures, can bend light, rendering objects invisible or focusing light beyond its diffraction limit. This control opens possibilities for nanoscale devices with extraordinary optical properties. Sensing the unseen. Plasmon polaritons as molecular detectives. Plasmon polaritons are powerful tools for sensing, capable of detecting single molecules. Their sensitivity to environmental changes makes them ideal for detecting trace amounts of substances. Applications span medicine, environmental monitoring, and food safety. Phonon polaritons, riding vibrational waves in crystals. Phonons, vibrations in crystals, couple with light to form phonon polaritons. These hybrid particles propagate through crystals, blending light and lattice vibrations. They offer unique insights into material properties and applications in sensing and communication. Tapping into the terahertz realm. Phonon polaritons are key in terahertz technology, generating and detecting terahertz radiation. They enable applications like non-invasive imaging and high-speed communication. Terahertz waves can penetrate materials, ideal for security and medical imaging. Guiding light with phonon polaritons. Phonon polaritons can guide light at infrared and terahertz frequencies. They offer advantages over conventional fibers, confining light to smaller dimensions. Applications include ultra-fast wireless networks and sensitive environmental sensors. Polariton condensation, a new state of light and matter. Polaritons can undergo condensation, behaving as a single quantum entity. This occurs at practical temperatures, offering unique properties like long-range coherence. Applications range from novel light sources to quantum information processing. Bose-Einstein condensation captivates physicists, manifesting quantum effects on a macroscopic scale. It leads to phenomena like superfluidity and superconductivity. These properties have potential applications in powerful magnets and quantum computers. The allure lies in its fundamental significance and revolutionary potential. The first realization of Bose-Einstein condensation in 1995 marked a new era. In 2006, Polariton condensation was observed in semiconductor microcavities. This opened possibilities for practical applications in lasers and quantum information. The field is rapidly evolving, pushing the boundaries of quantum exploration. We stand at the cusp of a new era in light-matter interaction. Polaritons enable ultra-fast optical computers, sensitive sensors, and quantum light sources. Applications include low-threshold lasers, optical switches, and quantum simulators. The promise of Polaritonics is to revolutionize technology by controlling light at the nanoscale. The journey into the Polariton realm has just begun. Challenges include achieving room temperature condensation and scalable fabrication. Advances in materials, science, and nanotechnology drive the field forward. Future applications include quantum computers and secure communication systems.